Okay, students, we are picking up, and this is, let me go back to the original page, we're talking about hyperbolic functions. These are hyperbolic trigonometric functions, so this whole other branch of trigonometry based around the hyperbolics, and they center and focus on the hyperbolic function x squared minus y squared in terms of deriving their values. But we'll just look at the functions themselves. So you see that we went through a few questions here, and we're going to pick up with example 4. We went through examples 1 through 3, and 1, 2, and 3, and now we're working on example 4 having to do with finding the equation of the tangent line to the graph of the function at the given point. So always remember that what you want to do when they ask a question like this is say, what do you want to end with? You know, you want your answer in the end to be a line, the equation of a line. And you also know that the line has an x value, negative 0.6, and then if you put the x value into the function, you get the y value or the point. So what you want for an answer is this equation right here, but it's not quite finished. So your first step is going to be, you got to get the slope, right? That's the only thing you need. So taking the derivative of the cosh is a sinh, but remember, you've got a chain rule here, so u is equal to 1 minus x cubed, and then du dx is going to be negative 3x. So you multiply, remember I said by the dinner, the derivative of the outer times the derivative of the inner, and then you're going to plug in negative 0.6. So when you plug in negative 0.6, then you see that you get this down here, and you get the dy dx is then equal to negative 1.66 for your answer. You go back to your point slope form. You're going to take that and dump in the slope, use the point slope equation form for the line, and there you have it. There is your equation. So if you notice to the side, I put the function value and the slope value as you calculated. You're going to, and you can see that here I have dy dx evaluated at negative 0.6 to give me the value of negative 1.66. Put it in the equation for a slope, and you're done. So I put the graph up here so you could see it, and the tangent line has to look right. Now, I didn't go ahead and calculate what the y-intercept would be. Certainly the slope is negative. Okay, and so it's probably a negative y-intercept or slightly negative. We can check that out with a graphing calculator. So now, in the next one, we're going to find any relative extrema of the function. Now, so the function is continuous, and if we look at this, we take the first derivative test and we say, all right, well, the cosh, it's always greater than 0, right? So for all its domain. So that's kind of nice that you're looking at it. So the slope exists, it's continuous, and it's greater than 0. So you know little things about the cosh. But then if you look at this, then you have, if you want to find the relative extrema, the first step is you're going to find the derivative. So we go ahead and get the derivative. So you have the product rule you use in the first grouping, and then you have the derivative of just the cosh. So what's interesting about this is that you take your derivative and you get off to the races and you go, oh, I get the product rule, first or second plus second or first. And then you realize that, oh, when we take the derivative of the cosh at the end, then we get minus sinh of x minus 1, and those two are going to cancel. So we end up with f prime of x is equal to just the x cosh of x minus 1. Okay, so there we have that. So we want to know, where is f prime of x equal to 0? First of all, you know that it's equal to 0 when x equal to 0, and when cosh x is equal to, cosh of x minus 1, sorry, x minus 1 is equal to 0. Okay, put those parentheses around. So we know both of those, right? So f prime equal to 0. So what I'm going to do is I'm going to say, well, cosh is always greater than 0, right? So what we're going to do is we're going to look at a number line as where is f prime equal to 0. We know at x is equal to 0, and we know cosh is always greater than 0. So we have two sides of 0 to pick. When x is equal to 0, this is one of our critical numbers, okay? And we know that cosh doesn't have any critical numbers because it's always positive. So if you're looking at our product here, then if I use a test point of negative 1 to the left of 0, and then a test point of 1 to the right of 0, you can see that f prime is here, f prime of x is then going to be less than 0, and that means that f is decreasing. And here, when I choose 1 as a test point, now think, it's going to be a positive 1, right? So that's the only thing determining the sign. F prime is greater than 0, so that means F is increasing. So what we're going to use is the first derivative test, and we're going to say, well, we have a minimum point there then, right? We have some extrema then. So since F of 1, and we can look at these, F of 1 turns out to be negative 1 times a positive, and F prime of 1, F prime of negative 1 is negative, F prime of 1 is positive, then we know that we have to have, and sometimes I draw it like this, it goes negative, then goes positive. So the slope is negative and positive. And then you can see right at this point, we have a min here, right? So as it turns out, we have a relative minimum, a relative min, we call it, at the point when x is equal to 0, but then y is equal to negative cosh of negative 1, I think, when you plug it in, because your function turns out, we have 0 times sinh of x minus 1, and then we just have minus cosh, so there's your point. So we have a relative minimum there at x equal to 0, and that is our point, okay? Whatever this is. Okay, and I don't have a function value for that, but you can get that easily. Then the next problem, so review that if you want to, go through each of the steps that you have. And I did put the graph off to the side so you would see what the graph looks like. And you can kind of see at the bottom where you have that, here's the horizontal tangent at x is equal to 0, and that would be your rel min. Okay, and let's look at this. So the next one, show that the function satisfies the differential equation. So this thing, a differential equation is just an equation with a derivative. This is called a second order differential equation because there is a second derivative in it. So you can see that in the first step, I take y prime, and then I take y double prime. And then I plug y double prime in, and then I subtract y from it. And you can see since they're identical, they're equal to 0. So we have shown, and every time you see that show thing, you've got to show by doing the work. You just can't say, well, because it is, okay? All right, next one. So now we're going to do some integration. So the integral of cosh is sinh plus c. This is the indefinite integral. So you can see I have a u substitution lined up here. And with the u substitution, I look at it and I say, well, we have 1 over square root of x, and that's part of the derivative of square root of x. You can say, all right, well, du is equal to, when u is equal to the square root of x, du is 1 over 2 square roots of x dx, and 2 times du is 1 over square root of x dx, which is what we have. So if you notice what I did, what's highlighted there in yellow in the original integral, I replaced with 2 du. Pass the 2 out front in the second step, and then after that, I'm just going to take the integral of cosh, which I get then sinh. So the hyperbolic sine u plus c, and then in the end, I'm just going to answer that. That's just going to be the hyperbolic sine. So equal to, and here's the answer to the integral, the original integral, then is 2 times the hyperbolic sine of u, which is the square root of x, and then plus c. Now, sometimes we really want to differentiate that these c's are different, but I think most students get it. It's still a constant that we don't know. But sometimes we like to differentiate that. Differentiate, maybe not a good word to use, but make it a C star and then a C for your final answer. There you go, there you have it. Okay, the next one is going to use the inverse trig integral, where you have the integral of du over a squared minus u squared. And in this case, u is going to equal sinh, and then du is equal to the cosh dx, okay? So we start off with this one, and we get our integral. So we're all ready to go, right? We just do a simple u sub here, and we know that a is equal to 9 because we have this formula up here that we have to, and a squared is equal to 9, and a is equal to 3. So then once we get that, we're just going to say, okay, well then that's arc sine of u over 3 plus c. Like I said, it's a different c, but no bother. And then we're going to put our u back in. Our u, remember, is sinh. So this is going to be the arc sine of sinh over 3 plus c. And then we're going to go to arc sine. We're going to put sinh in here as its exponential function. So we get the hyperbolic, or arc sine of the hyperbolic sine. So it's going to be e to the x minus e to the negative x, and that's over 2, and then that's over 3 plus c. Okay, and then we're going to scrunch this a little bit. And then we're going to put our final answer. So our final answer then is going to be arcsine. So the integral of all this turns out to just be arcsine of the quantity e to the x minus e to the negative x over 6 plus c, the arbitrary constant. Okay. Okay, and there you go. Moving on, we have the integral of cosh squared, but this is now a definite integral. You go from 0 to 1. And so we start off with cosh squared, but we're using a power reduction formula you see here. And so you can see that is up above. It's the hyperbolic cosh squared is equal to 1 plus the hyperbolic cosh 2x over 2. And that is exactly like the regular trig, which is cosine squared is equal to cosine squared x is equal to 1 plus cosine 2x over 2. So very similar here, so it helps you to remember all the new stuff. So the first thing I do is I put it in the integral, and I substitute cosh squared with what you see there, cosh squared of x with that. And then I'm going to pull out the factor of 1/2. It makes it a little easier. And then I'm going to distribute, or not distribute, but I'm going to use the sum, the integral of the sum is equal to the sum of the two integrals, okay? So there we have it. Okay, now I'm going to go ahead and integrate. So I get the integral of 1 is just x, so it's just going to be x over 2. And remember, I'm in x's now, so I didn't put these on here. I could go back and put them on 0, 1, 0, 1, and 0, 1. Okay, so I'm not changing variables at all here, 0, 1 up here too. So we have x over 2, that's going to be evaluated at 0 to 1, and then it's going to be 1/2 times, we know when we integrate, we're going to multiply by another half here. So this is going to be sinh x, 2x, sorry, sinh 2x. Did I forget an h? I did forget an h. So the integral, oh, and I forgot it here too. Yeah, let me go back here for a second and write that. That's the only one that I think I'm going to have to fix. Gosh, the other one's okay. Okay, so the hyperbolic sinh of 2x then, boom, boom, over 4, okay, because you're going to have that simple little use of where you have du is equal to 2 dx and so on. You're going to divide by 2. And then we're going to evaluate that from 0 to 1. Okay, so we have both of those, and we end up with, when we evaluate this, we're going to get 1/2 minus 0 over 2. And then we're going to get plus, you have the sinh of 2, putting 1 in, over 4. And that's going to be minus the sinh of 0, and that's going to be 0 over 4. So our final answer for these is 1/2. So our integral that you see up above is equal to 1/2, and that's in the beginning here. And then plus 0, that's gone. This is gone. So you have 1/2 plus, what do we have there? Did I forget something? Sinh of 2 over 4, maybe? I think sinh of 2 over 4. Sinh of 2 over 4, right? Okay, just need to look at that for just a second, okay? Maybe I'll come back to this in terms of how it turned out. But, okay, so I'm going to try to get this one more in because it's pretty quick, and then I'm going to have to stop at that point. So we have the integral is a definite integral of 1 over 25 minus square root of 25 minus x squared. So I'm going to look at this, I'm going to say, all right, this is 0 to 4 of dx over, and I recognize that you got that the square root, and I got that constant squared, 5 squared minus x squared. And I'm thinking already arcsine. So that looks exactly like the arcsine. Arcsine of x over 5 plus c, or no, not plus c, it's a definite integral. So we're just going to evaluate that from x is equal to 0 to 4. It is exactly the arcsine form. So we get arcsine. Just threw in the regular trig just to confuse you, minus, and then the arcsine of x over 5, you're putting 0 in, 0 over 5, right? Now, this one is going to be the arcsine of 0, so that one's just going to go, the angle whose sine is 0 is 0, right? And then your final answer then is going to be arcsine of 4/5. There you have it. There you go. There it is. So I'm getting pretty far along in this, so I don't want to go too far. And you can see that I have this other one. Here's number 11, so I can go over this pretty quickly and then sign out. But I've got a few more to go. Maybe I'll catch up with that in the class next week. But if you're looking at this, you have a y prime to get. You want to get the derivative. So I take y prime. Here is the formula for the derivative of tangent inverse. But we have a u sub where the inside function is sine 2x, a trig function. So now we're going to mix the trig with the hyperbolic trig. Good stuff, right? So u is equal to sine 2x, the inner function. Du dx is 2 cosine 2x. And then the derivative of the tangent inverse of u is then going to be u prime over 1 minus u squared. Now, you also know that you have 1 minus sine squared is equal to cosine squared, right? So we're going to use that identity in the end. Okay, here we go. So first step, plug in. You got your u prime is from here. You got u prime is equal to 2 cosine 2x. That's going to be the derivative of sine 2x. And then we replace the u in the bottom with sine 2x. Square it. That's sine squared 2x. And then we know the denominator then is cosine squared 2x. So now simplifying further, we know that we have 2 in the top, but we can cancel one of the cosines. Cosine, this one will cancel. So we only have cosine 2x in the denominator. So that would be our answer, 2 over cosine 2x. Now, very often, though, we like to do this because we're fancy like that. We would say y prime is equal to 2 times secant 2x, if you desire. But other times, we like to keep our expressions in terms of just cosine. Doesn't matter. It's preference. Okay, the next one I'm going to have you look at and try. If I don't get another video, I want you to try the limits. But the key here is not working with the trig, hyperbolic trig identity so much as changing over to x's, and then it becomes very, very easy. I will take one step with this, then I really got to get off. This video is going to get too long. The limit as x approaches infinity is going to be, you would handle it like this: e to the x minus 1 over e to the x over e to the x plus, because the bottom is cosh, right? 1 over e to the x, right? And as you go through these, then you realize that, oh, this is really, these two things are going to go to 0, right? Those are going to go to 0 on the limits. You know they are because you're going to infinity. So you could say e to the infinity, think of it as this, e to the x. You could separate these limits, actually. What you could do is take the limit of the top and the limit of the bottom, and you would have e to the x. It's always going to be e to the x minus 0 over e, and e to the x minus 0. If you're going to take the limits, whatever you get, you're going to get e to the x. That this thing is going to be 1. And I know you're thinking, well, this thing is indeterminate, right? But the thing of it is that fraction, 1 over e to the x, is going to go to 0 when you go to infinity. But e to the x is on your approach will be over e to the same number. Even though it's indeterminate, you can reason, and there's enough proof to say, this is going to be equal to 1. Okay? All right, couple notes on the last couple ones, and I'll go. So you have a formula to use for the integral, when you see it like this is the formula that you will use for number 13. Strictly formula, and it's one of those identities in the back of your book where you have the long formula list, okay? So you have to figure out what A is, and A turns out to be 3. When you do these, A is 3. And U in this case is, I have it already. U is x squared. It's given. So you plug it in there to get the form, and then you use the formula. For this last one, we're going to separate the differentials and integrate. Oh, no, we're not. No, we're not. We're going to have to use long division for this one. So I'm going to hold on to this one, okay? And I'm going to say sayonara because there's just too much, all right? But you have enough to probably go back and do the homework that I covered enough of these problems that you're kind of, okay, I kind of understand it. What I would suggest you do, though, in section 2.9 is go through them and make sure if you need to rewind, go through each of the problems slowly. You can even slow it down. So I'm talking really slowly, okay? I want you to have a great weekend, and I will see you Monday in class. Thanks. Bye.